right now. Okay, thanks for reminding me. And I will post it. Okay, I'll share the screen again. Okay, so let's see. I think it's down. It's probably way down here. Yeah, here it is. PDF text files for only for first 2 chapters. So you can always read the second chapter here and the first chapter for that matter. But I do encourage you to get a copy of the book or find the broken copy or whatever. Okay, so we're continuing to work on chapter 2, and hopefully that'll give us a good jump start on Verilog for those of you that haven't ever really looked at it. I know some of you have, and that's good. And some of you are in a couple of other courses where you're being exposed to it. All good. And you'll pick up the basics fairly quickly, and then we'll work on, fine tuning some of the details. Okay, let me decrease that, and let me decrease that, and we'll go over here. And I believe, yeah, okay. And here's where we left off. So we talked about, we were talking about the adder and how we can take the full adder module, which we can define like this. So basically, here's the full adder module. So this adds 1 bit of X to 1 bit of Y to 1 bit of carry in and generates a 1 bit carry out and a 1 bit sum. Now obviously, depending on the values of X, Y, and carry in, determine the values of the carry out and the sum. Carry out obviously could be 0, sum could be 0. If these all 0, they'll all be zeros. And they're set up this way. And then this module, once you create it, and again, you don't create it inside anything else. It's just part of your file. It stands alone because it's a module definition, just like a function definition stands alone. But unlike in C, you don't have to have function. You don't have to have module prototypes. You can put your top level module first, and you can put all your other modules after it, and the compiler will go through because it's a multi-pass compiler. And unlike C, that is supposed to be a 1-pass compiler, so you have to have function prototypes. None of which ever made any sense to me, but that's how C is set up. So anyway, so we just put the top level module first typically, and then we put all the additional modules we're going to use anywhere in the program. And then this module then can be instantiated anywhere you want. And when you instantiate it, you can follow, you have to make sure that your list of variables follows how they're defined in your module definition. Or you can use what's called the dot notation, which we haven't talked about yet, but we'll eventually cover that. And when you put the variable, when you instantiate it, you obviously change these variables to be the variables you're interested in, as opposed to what's in the module here, just as these are just sort of placeholders for the module itself. And again, since you're using positional notation, then you have to follow X has to be here, Y has to be here, carry in, C out, and sum in that order exactly, with none of the variables omitted. They all have to be included. And if you don't, if there's some variable you're really not interested in, like if you know there's no carry in, you could put a constant 0 here, or you could put a dummy variable and set it equal to 0, but you have to populate that spot. Okay, and then this is one way to do the module list, the port list for the module. Put the variables in parentheses, and then down here you define them, because you didn't specify that they were registers, then they're by default wires. Certainly it would have been appropriate to put output wire, C out, sum, input wire, X, Y, carry in. But anyway, that's not what happened. Remember, in continuous assignment statements, the left-hand side must be a wire. The right-hand side can be a wire or a register. In a always block, the left-hand side has to be a register, and the right-hand side can be other stuff. It can be a wire or a register. This of course is the operator for exclusive OR. So it's X exclusive OR with Y exclusive OR with carry in. And notice there is no double arrow, because there is no such thing as a logical exclusive OR. You have to think about that for a little bit, but makes a lot of sense. There is no logical exclusive OR. And then we have here because these are single bits, we can use the logical operators. But again, I personally don't like that, because then if you go back and change these to vectors, this is wrong and has to be changed to single ampersands and single bars for the bitwise operator. Because with vectors, you must use the bitwise operator if that's what you intend, which is clearly what you do intend in this operation. Okay, now what we're going to do is we're going to take this module and we're going to instantiate it so you can see how instantiation works. Now remember, for all practical purposes, we probably wouldn't do this, because what we would do in our top level module, or wherever we wanted to use this, instead what we would do is just write Cout appended the sum equals x plus y plus carry in. I mean, that's all you have to do, and you've done this whole thing that we're going to show you. But let's say you want to put some special features in this module and you don't want to let the synthesizer make some decisions for you, then you might want to specify it. All right. Anyway, so here's our 4-bit adder. This is going to be a 4-bit carry ripple adder, and what we're going to do is we're going to daisy chain 4 of the full adder single bit modules together to make a 4-bit adder, just like we did in logic design. And remember, so let me ask, is this a combinational or is this a sequential device?
Combination.
That's right. It certainly is. But if we actually built this into, sometimes we actually will, well, it is combinational for sure. But we can, there are times when some of our combinational devices will include a clock, not particularly in this case, because our FPGA sometimes behaves much better if you go ahead and put a clock, include a clock edge in your in what could be a combinational device, and you make it a sequential device, and then the FPGA is just happier with that. We'll see that later. All right. Anyway, these are internal signals within this top level module that don't appear in its port list, but the stuff that is in its port list will be used for the signals in the single bit adders, in the 4 single bit adders that we're going to instantiate. So remember back here, our variables were named X, Y, carry in, carry out, or CN, Cout, and sum. But when we actually instantiate it, like we're going to do here, notice we have different signals. We create a 4-bit vector for A, B, and sum, and single bits for carry out and carry in. And here we create 3 internal wires that we're going to use for the internal carries, C1, C2, and C3. C0 will be the same as this carry in, CI, and C5 or C4 would be the same as this carry out. So it already exists as a variable in the port list that's going to appear to the outside world. But these internal signals don't, and so that's why we have to create this wire. Notice same thing here. Here we have our variables. Here we list what they are, and if they're vectors, we also indicate that. Again, because we didn't say all these are going to be wires, and then we do designate this as a wire. And then finally, we do our 4 instantiations, and that's the end of the module. And each instantiation uses the module name. So back here, our module name was full adder. But in addition to that, we also have this FA0, FA1, FA2, FA3. Does anybody remember what we said this was?
Submodule?
Say again, Ahmed?
Submodule?
It's a unique name given to each instantiation. And the reason that that's done is because sometimes there are commands that we want to issue that can go in and find this unique instantiation and modify it depending on how we set it up. In this particular case, we didn't make anything that could be changed that way. but we could have created parameters and other things in the original single bit module that you could then modify by referencing this unique instantiation. And it's required. You have to have it. So that's why we have FA0, 1, 2, and 3. You could have called this X0. You could have called this, top 0, 1, 2, 3, or whatever. It's just completely arbitrary. You make this up, but it has to be unique. Okay, and can't appear in any other module either. Well, I guess it could actually. All right. So anyway, so then notice our variables, and again, what I want you to see is how when we go back to the actual port list that we laid out here. So it's X, Y, carry in, carry out, sum. So we have to follow that order. So this is X, that's Y. So our A is going to be X, B is going to be Y. Here's our carry in, that's the CN from the external world. And then our carry out is going to be one of these internal signals, C1. So it's C1 right there. And then our sum is sum 0. And again, A1, B1, sum 1. And then we have this first carry. And then the new carry out is the carry 2. And here the carry 2 is the carry in, the carry out is the carry 3. Here the carry 3 is the carry in. And the out is C out, which also appears up here as one of our external signals. And then we have A0 through 3, B0 through 3, and sum 0 through 3. So this is so this problem will very likely show up on the first, not on the logic design test, but on the first written test. And so I'll probably have you instantiate something where you have to figure out how to change these variables so that this works correctly. Okay. This is the named association, and we call it the dot notation because there's a dot X, and this dot X is the original name in the module definition, and then this is the signal we want to associate with it, and so forth. And in this case, they've lined the named association up in the proper order, but you don't have to. You can mix these up in any order you want, because with the dot variable associated here, with the new variable in parentheses, you can make the proper connection. And here you can leave a signal blank if you want, although that can create some confusion, so it's probably not a good idea. But you could actually do that. It won't totally spaz out. Okay, here's an example of. So remember here, our signals are outputs or inputs, but there is also a thing called a bidirectional signal, or an in-out. And so here's where we're going to talk. There are definitely statements that you can write that are legal, that may or may not give you an error, that may or may not compile correctly or synthesize correctly, if you want to call it that, and that may or may not simulate correctly. They might compile, they might simulate, but they might not give you what you intended. All right, so you have to be kind of alert. So here's an example. We have 2 gates. We have 5 variables, A, B, C, D, E. Inputs A, B, C, outputs D, E. And here they are. But notice one of the little confusing things. D is an input here. So if you write it like this, then this D, well, because remember, these are continuous assignments, right? So anytime the right side changes, you recompute this. And so when say if A changes, then you recompute D. If D changes, then you'd recompute this one. Even though D is theoretically an output, in this statement, it is an input. So is that okay? Well, so most of the time, yes, it's okay. It wouldn't be legal in VHDL. But if there are other modules that are also going to use D as an input to this module, then it has to be an in-out. So this could be a problem, or it might not be a problem. It depends on how you're going to instantiate this and how you're going to use the variable D. So this is one of the subtleties that you have to be alert for. All right, so you could do it like this, where you intend for D to potentially be an input. Now, and that of course is also a little bit tricky, because then this D here can be driven by the input, and it's also driven by the values of A and B, which is problematic too. And so then that makes D potentially be a 2-port variable. And so this is one of the problems you get into in Verilog, because remember, this is happening all the time. So you could specify D someplace else, but if A and B change, this would conflict then with the definition of D coming from some other place. And if you think about that as a hardware example, you could create a short circuit where one gate's trying to make D 5 volts and the other gate's trying to make it 0 volts, or 1.8 volts and 0 volts, or whatever. So you always have to keep in mind, you really cannot change these things in multiple places and expect it to work correctly.
Hello.
Yeah.
Would it throw an error if you were to leave it as a output D and then use it as an input D somewhere else?
So that's a great question. And the answer is it might not, and it might. It certainly is compiler dependent or synthesizer dependent, and you just can't be confident for sure how that's going to work. That's where you have to be smarter than the machine. I think in Vivado that we're going to use, what a really smart thing to do would be just to try that when you're in lab. You can play around with some of these some of these modules that we're going to create and use, and you can try a few things like this and see what in fact it does say to you. Chances are good that it might actually give you an error here, or that this might work okay, but it might let you know that you're changing D in multiple places. So it's possible you could have your hardware, your whole design could be such that A and B would never assign D a different value than you're going to assign it from some other module. But only you as the programmer, as the designer, can know that. And the compiler may not be able to figure that out. So the answer to your question is maybe and maybe not. All right. So I've mentioned this before. So we have two types of assignment operators. One that results in combinational logic, called continuous assignments, and it appears anywhere in your module as long as it's outside of a procedural block. And then you have procedural assignments that only appear inside procedural blocks. And again, there are two procedural blocks, always blocks, which are the most common. That's what we use mostly. And then initial blocks, which we can sometimes use we use them all the time in our test benches, which we haven't really gotten to. But what our test bench is set up to do is to create our simulations. But if we just put an initial block in our top level module, when we're working with an FPGA, that actually can be used. But if you're actually making an integrated circuit, you can't use it because you can't guarantee what any value is going to be when you power up the chip. When you power up an FPGA, because you're going to actually load a bit file into it, you do get to set the initial values, at least a lot of them. But in an integrated circuit, unless you build in initialization hardware to force flip-flops and other things into defined initial states, it will just power up in whatever random state it powers up in. Okay, so we talk about, this is a silly distinction. I don't really understand it. They say a continuous assignment is explicit if you put in the assigned word, and it's implicit if you don't. But what difference does it make? The point is you don't have to put the assigned keyword in. But I think it's smart to do it because it just kind of keeps you straight. Okay. So procedural assignments that appear in always blocks or initial blocks are always, they're synchronized to some other variable. Typically it's a clock. It's really rare for it to not be a clock, but you could have it, synchronized to some pin or something, but typically it's going to be a clock. And so the synthesizer uses built-in primitives to model this functionality, which would be like edge triggered flip-flops and whatnot. And this causes this causes some issues with your syntax. So 2 types of procedural assignments: the initial block and always blocks. The initial block is just what it sounds like. It initializes stuff. So it executes one time at time 0 in your simulation. And then that's it, it's done. And we can use it in test benches and in FPGAs, but you can't use it in integrated circuits that you're going to fabricate because you can't guarantee that initial state. Now, there is a whole science of how you build initialization hardware for an integrated circuit to put it into a fixed initial state. And it turns out these initialization hardware is really tricky because it usually relies on capacitors and things like that, holding lines low, but it's difficult to fabricate those in big enough values to really make it work well. And so then you resort to all sorts of other things and clear lines and other stuff, and it just gets really crazy. So it's quite a sophisticated part of integrated circuit design, and certainly not one that novices are going to be any good at. Certainly not me, that's for sure. So you have to approach that with some real fear and trepidation in your thinking, and make sure if you get stuck with trying to do that you get help from somebody that knows what they're doing, because it's definitely tricky. But for FPGAs, we do get to set the initial state because we load a bit file into it. And so we can use initial blocks in the code that we intend to be synthesized, as well as in our test benches, which are, of course, never synthesized. They're only used for simulation. Okay, then we have always blocks, which we use all the time. And always blocks execute basically whenever the signal in their sensitivity list is triggered. And you should remember that sensitivity list thing from logic design. They may execute at time 0. And if that's the case, sometimes there can be a race between an initial block and an always block that are setting the same signal. So that can be tricky. So again, you have to be careful with that. Always blocks wait for the event, whereas the initial block just executes. And here's what the initial block looks like. You have the keyword initial, a begin, a bunch of sequential statements, and the end. And again, we usually use this to set up initial values. The always statement looks like this. You have the always keyword, an @ sign, an @ symbol or whatever, and then you have in parentheses the list of variables, and they should be edge variables in almost every case. You cannot mix in Vivado. You can't mix edge variables and level variables. They all have to either be edge variables or they all have to be level variables. And if they're level variables, typically Vivado is thinking what you mean is that this won't really result in sequential logic. It will result in a combinational logic, and you're just using this always block in a bastardized manner, which you might think, well, why would you want to do that? Well, because you get some syntactic advantages when you do that, because you can use if statements. If statements can only be used in always blocks. You can use switch statements. They can only be used in always blocks. But you might actually intend them to just be combinational logic, in which case you can use this construct. But again, you do that. It's done all the time, but it's a little, when you're first starting out, you can definitely confuse yourself. So make sure you're very clear in your mind if you use an always block, if you're really planning on using it for sequential, resulting in sequential logic. Okay, so in the sensitivity list, if you have variables A, B, C, then it would execute whenever A, B, or C changes. But remember, we almost always will designate an edge if it's real sequential logic. Sometimes, instead of using commas, the old notation was A or B or C. It doesn't matter. Since 2001, the comma is totally legal, And I discourage the use of or because it's old syntax and probably eventually may go away. I don't know, but anyway, it's confusing. So just put commas. Okay. But you'll see that or used sometimes. So don't let that confuse you. It's essentially all it is really is a comma. Okay, so concurrent statements are used in an always block. They become sequential. So we put what look like continuous assignments in an always block, like C equals A and with B, but in an always block, it's considered sequential. Now, we're going to talk a little bit about this equal sign here. It turns out we have two different assignment operators in an always block. We have the equal sign, and then we have the less than equal sign. And they work differently. The equal sign is called blocking, and the other one's called non-blocking, and we'll talk about that. But so you do have to sort of pay attention. So remember, what looks like a standard assignment statement can definitely be in an always block, but when it's in an always block, it is no longer a continuous assignment statement. It is a sequential statement in general. Now, again, there is the bastardized use where you actually intend it to result in a combinational continuous assignment, and it will. But most of the time, when we have edge signals in this sensitivity list, then we're not going to use the equal sign. Most of the time, we're going to use the less than equal sign. And when you use level signals, then you probably are going to use the equal sign, and we'll get around to that. Okay, because these appear in this always block, when the right-hand side changes, well, so so usually the way this always block would be set up, you'd have a clock signal here. You'd have a positive edge of clock, pause edge clock. That would be it. You wouldn't have ABCD here. Because the way it's set up, because A, B, C, and D are in the sensitivity list, anytime any of these signals change, they will execute the always block. So these are going to function very similar to just standard assignment statements. Now notice here, you have when if A changes, then you execute the always block and you assign this to C. What value gets used here for C? Is it the same value, or how does that work? Because in an always block, if you use the equal sign, the order can matter. And so that's, again, it gets kind of confusing. And I don't know why. In VHDL, they did not allow this. There's a very strict distinction between a procedural block and the rest of the code. And procedural blocks never result in combinational code. But Verilog is just more permissive, it's loosey-goosey, and it does let you do things like that. Okay, so note, here we have level signals. And again, you can't mix edge signals and level signals. And now that's not necessarily true in some of the other synthesizers for Verilog code. If you're running Cadence, it may very well let you do that. But Cadence is typically used to make an integrated circuit as opposed to programming FPGA. So that's partly that distinction. But in Vivado, you can't. You cannot mix level and edge signals in the sensitivity list. Okay. So now we're going to talk about this idea of this bastardized use of always blocks, where you actually intend combinational logic, but you're using an always block. So always blocks can model both combinational and sequential logic. And that's why you have to be very careful with combinational logic, because if you make a mistake and don't cover all the possible cases, then it will result in sequential logic you didn't intend. It creates what's called a latch that you didn't expect. So, so here we have a module called no gates. We have these variables, A, B, C are inputs, D and E are outputs. And now notice here, we could have put register input or register output for D and E, but we didn't put it up here, but we can put it down here. And what that means is D and E are registers. A, B, and C are wires. Now, the reason A, B, and C have to be wires is because they're driven by the inputs. So these are driven from some external gates driving these. So these just need to be wires. But D and E are outputs, and they have to potentially hold their value. So we have to call them registers. In this case, they're not going to result in a register, but we have to call them registers because we're going to put them on the left-hand side in this always block. And remember, in an always block, the left-hand side must always be a register. So that's why it's set up this way. Now, notice here, they didn't use commas. They used that R notation. So don't use that. Just put commas. I think the R's look stupid there. For one thing, it's not even the right keyword for R because this is the R keyword. So I don't know. I don't like it. I think it's dumb. But that's how they used to do it until they changed it in, what was it, 01? Okay. So we have this statement, D equals A ORed with B, and E equals C ORed with D. Again, they're using logical ORs here, but because they're bit variables, because none of these were set up as vectors, they're all single bit variables. So we did specify a delay, which is fine. And we use the equal sign and not the less than equal sign. Because these are level signals, and we use the equal sign, your first impression should be this is probably intended to result in combinational logic. And in fact, that's right. Let's see. So this always executes once when any of the signals in the sensitivity list change. In this case, D is not in the sensitivity list, just A, B, and C. And that's how they set it up. And what that sort of means is they're not going to drive D from the outside. So D is more of an internal signal here, but it does show up in the port list. All right. And it's also it's designated as an output, not as an in-out. Okay. E stays at the O value even though D changes. So for instance, if D changes if it's changed on the outside somewhere, it's not going to trigger execution of this always block. So E wouldn't change until A, B, or C changed, and then it would recompute both these lines. All right, blocking and non-blocking. I mentioned this earlier, and here we have it. Sequential statements can be evaluated in two different ways in Verilog. Okay, sequential statements. That means we're only talking about stuff in always blocks now. Or I guess you are in initial blocks. So when they're in always blocks or initial blocks, if we use the equal operator, it is considered a blocking assignment. And if we use the less than equal sign, it is a non-blocking assignment. Now, just as a good rule of thumb, but sometimes there are exceptions. Whenever you use this always block with the intent to result in combinational logic, you should always use the regular equal sign. And you should use level signals in the sensitivity list. But when you definitely intend for sequential logic to come out of your always block, then you want to use this non-blocking operator most of the time. And we'll explain the difference. All right, so the blocking operator has to completely finish before the next statement is executed. So this is an exception. In this, when you use blocking statements, the order that the statements appear in your always block or your initial block matters. Normally, outside of our process blocks, always blocks and initial blocks, the order of our continuous assignment statements does not matter. But inside those procedural blocks, initial blocks and always blocks, if you're using blocking statements, just the equal sign, it does matter. However, if you're using the less than equal sign, then the order again goes back to be doesn't matter. However, you can mix these things. so if you mix them, then the order matters with respect to the equal signs. So it's a little tricky, but if you just keep that, what I just said in mind, you can keep it straight. So the non-blocking statement allows you to evaluate assignments without blocking the sequential flow. In other words, several assignments are evaluated at the same time. So whatever you have in your always block that's set up like this will all execute simultaneously, unless there's a blocking operator stuck in the middle somewhere. Then that would screw that up. Normally you want only non-blocking statements in your always block or blocking statements. You generally don't want to mix them, but there are cases where I've mixed them, and that was the only way I could figure out how to do what I wanted to do. So sometimes that does happen, but that's kind of rare. And when you use the blocking statements, you're normally not intending it to result in sequential logic. When you use the non-blocking statement, you normally are intending it to result in a sequential logic based on edge signals, typically a clock. Okay, so here's an example of blocking and non-blocking, and you can begin to see why this could make a difference. So we have a module, and within this module we have two always blocks. Notice these have clock edges. They have edge signals in the sensitivity list, and the way we call our edge signals, we call pos edge or POS edge or NEG edge. So this pos edge is a keyword, and we put it in front of the signal we want to make an edge signal. So this always block will not execute on a falling edge. It'll only execute on a rising edge. And so with this one of the signal clock in this case. Then here we have the equal sign only. So these are blocking. And here we have the less than equal sign. So these are non-blocking. Now, here's the way this works. In this always block, when clock changes, both these always blocks are going to execute simultaneously. In this one, B is going to be assigned to A, but there's a 10 nanosecond delay. So that 10 nanosecond delay will run completely, well, in the simulation. Of course, remember, these timing delays only count in your simulation. When you actually make your hardware, you don't get to tell the hardware how its quantum mechanics is going to work. That's up to what the hardware really is. So the hardware may execute a lot faster than 10 nanoseconds. It may execute a lot slower. So it just depends on the hardware. You don't get to write some number in there and then the synthesizer somehow magically make hardware that's going to behave that way. You do have some control over that, but when you're making an integrated circuit, you can pick the type of transistors you're going to use and the voltage you're going to run it at and the feature size, and that will relate directly to your timing delays, your inertial delay or propagation delay here. But changing this number does not change how the integrated circuit would be made. That's done with other mechanisms. Since I haven't designed integrated circuits, I don't actually, I haven't done that. But that's a different step. When you're programming FPGAs, the same thing. You can put whatever number you want, and it will be used in your simulation. But when you actually generate your bit file, no part of that propagation delay is going to be included in your bit file, because you're sending a bit file to a chip that's already made, and that chip already has characteristic speeds of its various gates, which you can't change now because it's already manufactured and it's done. It's existing and it functions at however fast it functions. What you can do is typically these FPGAs will have speed ratings on them, and you can pay a little more money and get one, or maybe pay a lot more money and get one with a higher speed rating, and your gate will run a little faster. But the number you write in here only has relevance for your simulation, has nothing to do with what's synthesized. Your bit file does not have that any of that delay information in it. Okay, so anyway, but what this does do though, when you execute this, B will be assigned to A first, And then the new value for A will be used here and assigned to B. So when this is all done, both A and B are going to have the same value. In this case, these will execute at the same time. And the original value of D will be assigned to C, and the original value of C will be assigned to D. So in this case, D and C are going to exchange their values. But if you take away this less than sign, then that's not what happens. Basically, B gets written into A, and it gets rewritten back into itself. So both A and B will have the value of B. Here, C will have the value of D, and D will have the value of C. They will have exchanged values. Here, they will have duplicated the value of B. So they certainly do result in a different outcome. Normally, this is what you want in a true procedural block. And normally, this is what you want in continuous assignment statements. But maybe not always. All right, yeah. So assume the initial values of A and C equal 1 and B and D equal 0. In this case, what's the value? What's the value of A and B at the end of this code?
One.
No, they'll both be 0.
Oh, 0.
Because B starts out as 0. So here A gets assigned 0, and here 0 gets assigned to B. Well, B was already 0, so now they're both 0. And what's the value of C and D when you get done with this code, when it runs?
C would be 0 and D would be 1. 1.
D would be 1. That's correct. Yeah, it's exactly what happens. Does everybody see that? Okay. All right. Okay, sensitivity list. Again, that's this thing right here in the parentheses in your always block. And sometimes we'll leave that out entirely and just put the @ sign with a star. And that means every variable that appears in the always block is assumed to be in the sensitivity list. And there's no edge signals. So that always occurs when you're doing combinational logic. So an always block will be activated if one of the events occurs. In combinational logic, the sensitivity list includes all the signals that are used in the conditional statement and all the signals on the right-hand side of the assignment. So what they're saying is, if you intend this to be combinational logic, you're using this in the bastardized sense, then make sure you put every signal that appears down here ought to be in the sensitivity list. Certainly on the right-hand side anyway, maybe not the left necessarily. But in a sequential circuit, contains 3 kinds of edge-triggered events: clock, reset, and set signals. So generally, that's all you put in your sensitivity list: the clock, a reset signal, or a set signal. And they're all edge-triggered. They're all edge signals. Again, in Vivado, you can't mix edge and level signals in the sensitivity list. I don't know about in Cadence. I think you probably can in Cadence. I don't actually know because I haven't used Cadence. But when you're making an integrated circuit, there's no reason why you wouldn't necessarily. There might be a case where you would want to do this and have these signals mixed. And I think Cadence will let you do that. But in FPGA, that's not true. When you're dealing with sequential logic in an FPGA, you're always dealing with flip-flops. So really, only edge, clock, reset, and set signals are relevant. And in the FPGA we use, they tell you you can have a reset or you can have a set, but don't have both unless you absolutely have to, because if you have both, then it definitely jacks up the efficiency of your logic. So you should never do that unless you absolutely have to, and then only where you have to. And that's because they have provision there's a one line that goes to the flip-flop, and it can be designated as a reset or a set. You don't have 2 lines. So if you want both, and it takes a fairly complicated circuit to get it. Okay, wire and register. We've talked about this, but here they're finally introducing it. While the data type wire can be used if only connection is needed between signals, the data type register is used where the assigned data needs to be stored until the next iteration of the statement, till next time the statement's executed. So that's a good way to think of it. So kind of put that in your mind. Register is there when you have to save the information until the next clock, or you have to save the information until the next time that signal gets recalculated. So if you want to assign your output in sequential code within an always block, not that you should declare it as a register, you must declare it as a register. And the reason for that is it's going to be on the left-hand side in an always block, it has to be a register. And if it's going to be on the left-hand side in an assignment statement outside of an always block, it has to be a wire. So wire can be used only in modeling combination logic and must be driven by something. Wire cannot be used as the left-hand side of an equal or less than equal in an always block. But here's what's really screwy. So you go ahead and designate your signal as a wire, as a register, and then you put it on the left-hand side with an equal sign with a blocking assignment in an always block. And the synthesizer will look at that and decide that what you really intended was combinational logic. So even though you declared your variable as a register, it will not make it a register. It will make it a wire and create a continuous assignment statement and not really have a procedural block at all in your final net list. So that's using it in this bastardized use where it results in something that it doesn't appear to be, which it drives me crazy. I've certainly done it, but I just encourage you to do it with fear and trepidation, because if you make a mistake, then it can't assign it as combinational logic. It has to make it sequential, and that can screw things up. Okay, the data type wire is the only legal type on the left-hand side of an assignment statement outside of the always block. All right, register can be used to model both combinational and sequential logic. Yeah, because if you model combinational logic with it, it never really gets created as a register. It gets created as a wire instead. So there you go. Register is the only legal type on the left-hand side of an equal or a less than equal in an always block. Register is the only legal type on the left-hand side in an initial block, which we normally use in test benches or to initialize an FPGA. And the register cannot be used on the left-hand side of an assign statement. There are a whole bunch of other data types that we're not going to really deal with. We'll mention them at the end, but for all intents and purposes, these are the only two you have to mess with. So a flip-flop. So a flip-flop is the quintessential sequential logic device, right? It's how we implement all of our high-speed memory in the operating cores of our various processors. That's true across the board. And so here's the Verilog code for a simple D flip-flop. Remember, the flip-flop can change state either on the rising edge or on the falling edge of the clock, but you usually have to pick one or the other. This type of behavior is modeled in Verilog by an always block. So here's your symbol. Clock, little cone means it's an edge clock. No bubble should mean it's a rising edge. Your D input and your Q output. Usually we also have a Q prime output. And here we have always at pause clock, pause edge of clock. Begin, Q is assigned the value of D. Notice non-blocking. Probably wouldn't really matter here because there's only one statement anyway, but you normally, when you have edge signals up here and you intend this to be sequential, you normally should discipline yourself to use the less than equal sign as the assignment operator inside the always block. Okay, does Q, what type of signal does Q have to be? Can it be a wire? No, it cannot be a wire. It must be a register. Remember, inside the always block, left-hand side must be a register. Outside the always block, left-hand side must be a wire. All right. Now, of course, this flip-flop has no set or clear. Let's see. I think I'll stop there. Well, maybe I'll mention this briefly, this transparent latch. So here we have a level situation where we have a latch. So these are not edge signals. And again, remember the or, just totally fine to should put a comma there instead. G, comma, D. Either one of those changes, it's going to execute. If G is true, then Q equals D. So this is a latch where when the gate is active high, then D is propagated directly through to Q. That's why D has to be in the sensitivity list also. Because if G is high, then the output will change when D changes. If G is low, inactive low, then the latch is closed and Q is held at its current value regardless of what D does. Okay, I'm going to stop with that. Let me give you just a minute to ask questions if anybody has any. Anybody have any burning questions? Have all of you gotten your Nexus 4 boards?
Yes.
Okay, good. The first homework is due. It's on the syllabus. Let me pull that back up. Due homework 1 due today, the 1st of September. So that would be Wednesday. Okay. It's all in the syllabus, all the due dates for the homework. And yeah.
And if we show up and display our demo, our lab, then we only need to turn in the lab report, correct? That's attached to the lab.
Yeah, you can upload that on Blackboard. Yeah, but remember, what really counts is your demo. You can do all the lab reports and still flunk this course. You have to demonstrate your code. And I'd like you to do that in person, but if you're, just as a consideration because of COVID, if you want to send Alex a video with your ID card and the picture demonstrating that your code's running, that's okay. But I would prefer you do it in person. And I encourage you to come to the lab. I know some of the labs are easy, but we may make some audible changes to labs on the fly. So be ready to, and I may, some of the labs may change. So don't be working, a month ahead. Just do the labs the week they're due. You can look at them ahead, but I may change them at the last minute. And I usually come into lab and talk for the first 30 minutes or so in lab. I'll kind of talk about the lab a little bit because there's certain things I want you to learn from each lab. And if you just blow through it, you may get it done, but you may not learn the part that we want you to learn. So we really want you to, engage in the lab. Let me just say, this is important stuff. If you can, and one of the things I'll probably do near the end of the course is give you the examples of some of the questions that get asked in interviews about Verilog. And you will realize that this is one of the areas people pimp you when they're trying to see how much you know. So this is in your interest to know this stuff so that you can secure a good job when you get out of here. This is important knowledge, and you're going to need to know this. This is going to become more and more important because we're moving to a time in a day when almost every device is going to have a microprocessor and an FPGA built into it, and they're probably going to be on the same piece of silicon. So this is where we're going.
Oh, and then so for when we start classes after the 3 weeks, will we actually meet in person for the lecture?
Yes.
Or is it still going?
No,
okay.
No, we'll do it in person.
Okay.
I think it'll be better. I think it'll be a lot better. I mean, this is okay, but I can't see a single one of you. So for all I know, you're watching videos on your other screen, and not that you would do that, but it'll allow me to call on you in class. It'll allow me to do a little better at keeping your attention. I tend to be a little more animated when I'm, performing for a class, and these tend to be a little more boring. I mean, this would put me to sleep. When I was at Purdue, this was exactly the thing. You know, videotaping had just kind of been invented. And so a lot of the professors are all excited to videotape their lectures and play them in these darkened rooms with little bitty black and white monitors mounted on several places across the front of the room. And they'd turn on the lights so you could actually see the TV. And I mean, I just go to sleep. It was ridiculous. They were so boring and terrible, all in black and white. So I know this isn't as compelling as in person, and that's why we're going to do in person.
Okay, and then for the, I do remember you stating that we needed to bring a SD card. Do we need to bring that 4Lab one?
No, you don't have to. I just recommend you do it because once you generate the bit file, then you may, so let's say you get it 90% done, and then you go home and then you finish it up and then you have a bit file. And so then what you can do is you can just put that bit file on the SD card. You can also do it on a jump drive too, actually. Put it in the root directory as a .bit with no other .bits there. And then you can plug it into the SD card slot, or you can plug your jump drive into the USB slot. And then when you come back to lab the next week, you can flip that out, plug it in, it'll instantly program your board. You can demo that, and then you can go and start your next lab without having to go all the way back through generating the bit file again and downloading it to your board, which can take, 5, 6, 7, 8 minutes for a simple program and much longer for something really complicated.
Okay, thank you.
So let's see. Yeah. Good morning. Remember to start recording. Thanks. How many instantiations can be done in a module? It's unlimited, infinite. Ahmed answered that. Thank you, Mark. Don't we have to use our module name when an instantiation along with unique identifier? Yes, you have to use both the module name and a unique identifier. Theoretically infinite, but hardware will limit. Sure, right. Yeah, there are always real world limits. There's only one infinite being, and that's God. Okay, link adder, 4F0, etc. Yeah, right. Full adder, instantiated full adder into the adder 4 module. Right. Okay, I wasn't looking at the whole screen. Thanks. 0, 0, 1. Where's the first homework due? September 1st, Wednesday. Not yet. I'm missing the board still. Oh, okay. So if you don't have the board, come get one. We have a few more left. If there may be a few people that wind up without one, but we are in the process of ordering 15 more, so we should be in good shape in a week or two. So if you wind up without a board, just buddy up with a friend and for the first couple of labs. Yeah. So bring, if you have an SD card, you can bring it, but it's not really needed for the first lab.
What size was the card again that you need that we should supply for?
Yeah, an 8 megabyte one will be fine. 16 megabytes should be fine. Maybe you better get a 16. I forget I think it's only like 3 megabytes is the size of the memory in the chip on our FPGA board, but I could be wrong about that. I know if you have a 16, it'll be fine. Probably an 8's fine too, but I don't remember for sure.
Okay.
I'd have to look it up. Labs due. Yeah, I want you to finish lab 1 this week. Does anyone else have their Blackboard set up where nothing shows up in their content folder? Yeah, I don't know about that. It should. I know when it should show up properly for you. And if it doesn't, call Blackboard and have them help you figure out what's going on. Yeah, it's all on the home page, right? The tab is the very bottom of the course page. Okay. Tab is called Digital Design, and all the content's there. That's right. Okay. In-person lectures are held only on Mondays, right? No, I will do lectures. What I might do is I will do in-person lectures pretty much every day, but there may be an occasional time on Friday where I either make cancel class because you really only have to have 2 lectures a week for this class, or I may have you watch one of the videos. But usually I'll lecture on Friday too. So plan on 3 lectures a week in person. Yeah, right. That's, yeah, John, got it right. Okay, very good. Okay, GB, I don't know who that is. Fuller called, thanks for that. Have a great day. Got to run, no problem. Okay, yep, that's it. So, so sounds good. I just wanted to go through the chats, make sure I didn't miss anything. Okay, we'll see you guys on, see you in lab this afternoon for those of you who come. And try and get lab 1 done this week. And we'll talk to you later. What was that?
The question for the gig, they're asking if it's gigabyte or for the SD card.
Yeah, like 16 gigs should be fine. Yeah, gigs, not megabytes. Yeah, not an 8 gigabyte SD card would be fine because I think it's a handful of megabytes.
Okay.
Yeah, so yeah, 1 gig should be fine. That's 1,000 megabytes. There's nowhere near it's that big. So yeah, an 8 gig card should be fine now that I think about it. Absolutely. All right, talk to you later.